Right triangle trigonometry. In section 5.3, we were introduced to the sine and cosine functions as ratios of the sides of a triangle drawn inside a circle, and spent the rest of that section discussing the role of those functions and finding points on the circle. In this section, we return to the triangle and explore the applications of the trigonometric functions to right triangles where circles may not be involved. Recall that we define sine and cosine as sine of theta equals y divided by r, cosine of theta equals x divided by r. Separating the triangle from the circle, we can make equivalent but more general definitions of the sine, cosine, and tangent on a right triangle. On the right triangle, we will label the hypotenuse as well as the side opposite the angle and the side adjacent next to the angle. Right triangle relationships. Given a right triangle with an angle of theta, sine of theta equals opposite divided by hypotenuse, cosine of theta equals adjacent divided by hypotenuse, tangent of theta equals opposite divided by adjacent. A common mnemonic for remembering these relationships is SOHCAHTOA, formed from the first letters of sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Example 1. Given the triangle shown, find the value of cosine of alpha. The side adjacent to the angle is 15 and the hypotenuse of the triangle is 17. So cosine of alpha equals adjacent divided by hypotenuse equals 15 divided by 17. When working with general right triangles, the same rules apply regardless of the orientation of the triangle. In fact, we can evaluate the sine and cosine of either the two acute angles in the triangle. Example 2. Use the triangle shown, evaluate cosine of alpha, sine of alpha, cosine of beta, and sine of beta. Cosine of alpha equals adjacent to alpha divided by hypotenuse equals 3/5. Sine of alpha equals opposite of alpha divided by hypotenuse equals 4/5. Cosine of beta equals adjacent to beta divided by hypotenuse equals 4/5. Sine of beta equals opposite beta divided by hypotenuse equals 3/5. You may have noticed that in the above example that cosine of alpha equals sine of beta and cosine of beta equals sine of alpha. This makes sense since the side opposite of alpha is adjacent to beta. Since the three angles in a triangle need to add to pi, or 180 degrees, then the other two angles must add to pi divided by 2, or 90 degrees. So beta equals pi divided by 2 minus alpha, and alpha equals pi divided by 2 minus beta. Since cosine of alpha equals sine of beta, then cosine of alpha equals sine of pi divided by 2 minus alpha. Cofunction identities. The cofunction identities for sine and cosine are cosine of theta equals sine of pi divided by 2 minus theta. Sine of theta equals cosine of pi divided by 2 minus theta. In the previous examples, we evaluate the sine and cosine on triangles where we knew all three sides of the triangle. Right triangle trigonometry becomes powerful when we start looking at triangles on which we know an angle but don't know all the sides. Example 3. Find the unknown sides of the triangle pictured here. Since sine of theta equals opposite divided by hypotenuse, sine of 30 degrees equals 7 divided by b. From this, we can solve for the side b. b sine of 30 degrees equals 7. b equals 7 divided by sine of 30 degrees. To obtain a value, we can evaluate the sign and simplify. b equals 7 divided by half equals 14. To find the value for side A, we can use the cosine or simply apply the Pythagorean theorem. A squared plus 7 squared equals b squared. A squared plus 7 squared equals 14 squared. A equals the square root of 147. Notice that if we know at least one of the non-right angles of a right triangle and one side, we can find the rest of the sides and angles. Example 4. To find the height of a tree, a person walks to a point 30 feet from the base of the tree and measure the angle from the ground to the top of the tree to be 57 degrees. Find the height of the tree. We can introduce a variable h to represent the height of the tree. The two sides of the triangle that are the most important to us are the side opposite the angle, the height of the tree we are looking for, and the adjacent side, the side we are told is 30 feet long. The trigonometric function which relates the side opposite of the angle and the side adjacent to the angle is the tangent. Tangent of 57 degrees equals opposite divided by adjacent equals h divided by 30. H equals 30 tangent of 57 degrees. H equals 30 tangent of 57 degrees, which is approximately 46.2 feet. The tree is approximately 46 feet tall. Example 5. A person standing on the roof of a 100-foot tall building is looking towards a skyscraper a few blocks away, wondering how tall it is. She measures the angle of declination from the roof of the building to the base of the skyscraper to be 20 degrees and the angle of inclination to the top of the skyscraper to be 42 degrees. To approach this problem, it would be good to start with a picture. Although we are interested in the height, h, of the skyscraper, it can be helpful to also label other unknown quantities in the picture. In this case, the horizontal distance, x between the buildings and A, the height of the skyscraper above the person. To start solving this problem, notice we have two right triangles. In the top triangle, we know one angle is 42 degrees, but we don't know any of the sides of the triangle, so we don't yet know enough to work with this triangle. In the lower right triangle, we know one angle is 20 degrees, and we know the vertical height measurement of 100 feet. Since we know these two pieces of information, we can solve for the unknown distance x. Tangent of 20 degrees equals opposite divided by adjacent equals 100 divided by x. X tangent of 20 degrees equals 100. X equals 100 divided by tangent of 20 degrees. Now that we have found the distance x, we know enough information to solve the top right triangle. Tangent of 42 degrees equals opposite divided by adjacent equals a divided by x equals a divided by 100 divided by tangent of 20 degrees. Tangent of 42 degrees equals a tangent of 20 degrees divided by 100. 100 tangent of 42 degrees equals a tangent of 20 degrees. 100 tangent of 42 degrees divided by tangent of 20 degrees equals a. Approximating a value, a equals 100 tangent of 42 degrees divided by tangent of 20 degrees is approximately 247.4 feet. Adding the height of the first building, we determine that the skyscraper is about 347 feet tall.